This is the first of two videos talking about inelastic collisions and explosions for day 16. So our first problem we're going to be looking at, we have an astronaut who has been floating away from their spaceship. So we've got the astronaut, and he's got his little air tank here, and he's floating away from his spaceship at a velocity of 2 meters per second. And that is a problem. His spaceship is currently a total of his rocket is a total of 10 meters away. And he currently has no way of returning to his rocket. He is floating out in space, eventually left for dead, which is a problem for him. So what he's going to do is he's going to take this can, and we'll call this second later. He's going to throw it such that the can of air, he's going to hold his breath and hope that this can of air, by throwing it such that its new velocity is 20 meters per second, will allow him, he's gone neon at this point, to float backwards towards his ship. And he's not sure, but he's hoping that he will get back there in time to get some oxygen and save his own life. So this is an explosion problem, because we start with two things together, and we have the mass of the astronaut, and we say that mass of the astronaut is 115 kilograms, including that giant suit he's wearing. And we have the mass of the oxygen tank that he's holding, which has a total of 15 kilograms. And he's hoping that by throwing it in the opposite direction from him, he's going to create some propulsion in order to throw him back. And in reality, that's what propulsion is. We're throwing stuff out as fast as we can behind us in order to propel us forward for rockets and everything like that. But that becomes a whole lot more difficult than the types of problems we're going to be working with. So this is a little bit closer to what we'll actually be working with in class for our non-calculus based class. So with this is a two-step problem that we're trying to do. And what we want to find is we would like to know what the velocity of the astronaut at time 1 is. And we'll call this time 0. We'll call this time 1 in this case. And we would like to know the amount of time to return to the ship. So T from, we'll call it from time 1 to times 2. Time 2 is the point where he makes it back to the spaceship, assuming he makes it back. So maybe part 2 of the problem is a spoiler for part 1 of the problem, but that is what we're trying to solve in this question. So let's have at it. In order to solve this, we are going to use our conservation of momentum equation for explosions. So we can say that the sum of momentum, which we could write as p, at time 1 is going to be time 0 is going to be the sum of our momentum at time 1. And if you watched the last video, or if you sat in class already for this, you know that I normally don't even write this out. I write in my sum of my masses times my momentums, and I just write mv, mass times velocity. Out is going to be the sum of my masses, at time 0 is going to be the sum of masses times my velocities at time 1. It's a lot simpler to write out. Makes it so that we've got one less letter that we have to always be taking care of. So with this, my masses and velocities at 0, we have my mass, the 0 looks like an O. We've got my mass of my oxygen and my mass of my astronaut. And they're currently together as one piece, and my velocity at time 0. Try to make it a little bit more 0-like, a little bit less round than the O. And that is going to become the mass of my oxygen and the velocity of the oxygen at time 1 plus the mass of my astronaut times the velocity of my astronaut at time 1. And in order to solve this, I have to have a directionality, and I'm going to say that towards the spaceship is my positive direction because that's where I want to go. So there we have it. Pretty simple equation set up there, and this is almost always what you can jump to for your explosion problems. This one's a little bit simpler in that we're working in 1D. So we only have the one equation, but we could break it into x and y components. So my mass of my oxygen tank is 15 kilograms. My mass of my astronaut is 115 kilograms. And the velocity at time 0 is a negative 2 meters per second. That's my left side of the equation. My right side of the equation, my mass of my oxygen tank is 15 kilograms. My velocity of my oxygen tank is negative 20 meters per second. My mass of my astronaut is 115 kilograms. My velocity of the astronaut is what I am solving for. Okay. Plugging all of that in. So we've got negative 2 times 130. So that should give me negative 260 kilogram meter per second. And then I've got 20 times 15. 2 times 15 is 30, so that is 300. And I'm going to subtract it to the other side, so minus a negative 300 kilogram meter per second is going to be 115 kilograms times velocity of the astronaut at time 1. This is negative because this was negative, and then I've got a minus because I subtracted it to move it to the other side of my equation. So negative 260 plus 300 is going to be 40 kilogram meter per second divided by 115 kilogram. Kilograms are going to cancel. We're going to end up with meters per second, which is exactly what we want. And that number for me comes out to value of 0.348 meters per second. And you notice it is positive, which means, yes, we are in fact returning to our ship. So positive 0.348 0.8 meters per second. Step 1, done. Step 2, how long does it take to get back? Well, force diagram, got my astronaut. He's got no forces on him. There's not even gravity. He's just floating out in space. Sum of forces is equal to mass times acceleration. We've got no forces at all, let alone in this direction. So sum of forces is 0. Acceleration is 0. So we can then jump into our kinematic equations, and we can say x at time 2 is going to be equal to x at time 1 plus velocity at time 1 times time plus 1/2 of my acceleration in the x times my time squared. This is all of the astronaut. I can put a little a in front of all of these. Acceleration I just went over was 0. My x position initially, let's say, is 0. And I'm trying to get to a position of 10 meters. I could call this guy 0 and I could call this guy -10, depending on how you want to define what's 0. So if this is 0, this is 0 plus 10 because this is 10 meters. If this is 0, this is 0 minus 10 because this is 10 meters and this is the positive direction. So that's 10, which is equal to the velocity of a of 1 in the x, which is 0.348 meters per second times my time. And my time comes out to 28.75 seconds. That's my time to return. And we really hope that an astronaut can hold their breath for almost 30 seconds. So throwing the gas can when they did was a great job, because if they started to get further away, that's a longer time. They have to hold their breath, but they've saved themselves from floating endlessly in space until they run out of oxygen anyways. So that is our explosion problem. Example problem. We will have another video for today that is going to be our inelastic collision problem. And that one we're going to work with 2 dimensions. So take care.